is part of my master thesis, supervised by Bürgisser. So first, let's start with what the formula is. Okay, so essentially a formula is just a string of symbols that algebraically makes sense. So, an example of a formula is, for example, this. Here a minus 1, here a y, z, 3. And an example of something that, for example, is not a formula, it's something like this. Okay. So here we will just consider formulas with addition, multiplication, and addition. And in this case, we will just care about the size of the formula. We will just be the number of algebraic operations that we have on the formula. For example, in that case, we have one multiplication, one addition, so this is 2. Then there is an inversion, this is 3. Then a product, this is 4. Then 5, and then 6. So the size of this formula is 6. Okay, so now the thing is, the bigger the size of a formula is, the more complicated it is to understand the rational function that this formula defines. So the thing is, everybody that probably have a lot of algebra classes, you can give them a lot of very weird formulas, very long ones, and the idea is how difficult it is really to understand what the formula is telling you. So essentially is, for example, I can give you a formula. One of the things that you might suspect is that I just given you the zero rational function encoded in a very complicated expression. And of course, what you want is really to check that I'm not giving to you the zero function encoded in a very large expression. So you want a fast way of decoding this. So this is essentially what is the polynomial identity testing. So essentially, given a formula phi, is it representing 0? So this is the main question that one is making to oneself, but one wants to do it in an efficient way. So essentially, you want to do it in polynomial, deterministic polynomial, with respect to size. Here there can be some details depending if you consider bit size or algebraic size, but this is not important for us now. And the things that are known, so the first observation is that the polynomial identity testing is in RP. So essentially this means you take a formula, you pick a random point, your favorite random point, you evaluate. If it is not 0, then you know that the formula was not 0. If it is 0, maybe you have been unlucky, and maybe the formula is still not representing something that is not 0, but you can never be sure. So you are only sure. And the second observation is, why is this important? And essentially the reason why this is important is because this problem is central on the randomization of algorithms. So once we have this, there are a theorem that this is a very classical theorem in algebraic complexity and other branches. So Balian, then there is the version of Kubret at Bürgisser of 2015, I think. And in this version, essentially what you do is you translate your formula in a kind of subspace of matrices. And you translate it to this problem. So essentially, given a subspace of matrices, is there non-singular matrix in this space? So this will be the problem that we will center in. Okay. So until here, we have reduced this polynomial to looking for non-singular matrices here. And now we go to the second point, which essentially is what is called the plane-rod analogy, which will play the central role in how you approach this. So essentially here we have two words that usually have. On the one half we have the discrete word, and on the other half we have the continuous word. And usually these discrete words appears in what is classical information theory, and this other word appears in what is quantum information theory. So the big difference is that here the basic object that you study is just a finite set S, while here what you study is a finite Hilbert space H. So essentially a vector space with an inner product. And many times, depending on the case, what one wants to consider is the projective space, because from a physical perspective you cannot distinguish points that differ on a multiplicative constant. And here you got like two models of relating this. So in one part here you have the lattice of subsets, here you have the lattice of superspaces. These lattices are really similar and different. This lattice is reflected in the non-negative cone, and this is reflected in the PSD cone. And then here we consider two kinds of operations. So here what we consider is first subjective partial functions. And the analogous of this is just linear maps. So this translates to this. And then what translates in the other way is, on the left, you have correspondences. So essentially ill-defined functions that set one point to something, maybe to nothing, maybe to several points at the same time. So essentially you usually represent this formally as a subset of here, of S times T, where if the pair SE is in this set, if and only if C sends S to T. And here you have what is called linear correspondence. Which essentially is just a subset, a sublinear superspace of this space of linear maps, which is essentially this tensor product. Okay. So we are interested in studying this and this as analogous. Okay. So at this point, the completely positive operators usually come into play on the right, and the other ones on the left. So in the classical setting, you have the stochastics map, which is a matrix of non-negative entries, which each entry giving you the probability of some transition happening. And this usually encodes the combinatorics of it, because if you are all interested, is there a non-zero probability of passing from this state to this other state, you give it with a correspondence. And in the quantum case, what you got, this is translated in a completely positive operator. And in this case, what you get is a linear correspondence, which is this kind of subspace of these matrices, where these A's usually represent the set of quantum states. And here there will be two guys that we will define, that will be C star and A star, which essentially this will be used to span all these guys. And this is used with T, so start CL, secant T, so S belonging to prime. Essentially, this associates to each subset the possible guys to which you can go applying this non-deterministic operation. So essentially here, everything that is here is the things that you can arrive from points in S prime, and another thing here is things that you can arrive from points in W. So this is a kind of non-deterministic model of quantum mechanics, and this is a non-deterministic model of classical mechanics, which you can go to something but not exactly. So once this is clear, now the theme is how we generalize this a step further, what is called quantum maxims. let's consider two bipartite graphs. Is any person familiar with combinatorics will notice that a correspondence can be used both as a kind of bipartite graph. Because essentially you can have something like this, and you can have something like this. So essentially you say how the things go from one set of points to the other, and the edges you say if it goes to the other or if it does not go, there is not an edge. So on the left we can see that here we have a maxim. And on the right, you can try and say, okay, there is not a matching, and usually if it is small enough, it is enough to say, try everything, if nothing works, it's done. But usually the best way is what is a hard block. So one notice that these two set of points and these two set of points, there is no edges going from here to here, and the combined size of this is bigger than the size of these 3 points. So if any kind of perfect matching will exist, you will need an arrow connected each one of these, and there should be an arrow connected this of this by the Pigeon Hole principle. Okay, so the problem is, okay, I can describe this, and then it's pretty clear what a hard block is, like a pair of subset, bigger, etc. But the problem is that this cannot be generalized to this setting. I mean, here it's clear that you can draw points and edges connected them. The problem is that try to draw a projective space and then deduce what is an edge that you have to draw. And probably you will enter in problems that there are not enough dimensions in this blackboard to draw whatever you can think that can be drawn. So what one does is one uses these things here, so all this formalization in order to deduce this. So then what one realizes is that a maxim of this C going from S to S is an injective partial function, because essentially it sends a pointer to nothing else. F that also goes to S should start for every S where F is defined, you are contained in these sets of the possible ones that S can go. And a half block is used a pair of subsets should start the two sets has more cardinals than the set that you are working in, and when you apply this, so you look everything that can go to here, this will be contained in the complement of S1. So this is an idea going back to Bürgisser in 2004, which is, let's just translate these two definitions formally to this case, using this analogy, and then we will get the definition of a quantum continuous matching of this. So essentially, a quantum continuous matching of these linear superspace of matrices will just become a linear matrix, and essentially a half block then will just be a pair of superspaces such that the dimensions is bigger than this dimension. And when I apply this similar to the image to the first H0, this is contained in the orthogonal complement of the other. Okay, so now one sees clearly that here we have, okay, a matching is just a matrix here. A perfect matching is a matching that has exactly the word size. So a perfect quantum matching will be just a non-singular matrix, so the biggest rank that you can get. And the thing is, when one looks at this problem here, one sees that this is exactly this. So essentially what you just realize is that this thing is essentially the same as quantum or continuous perfect matching problem. So at this point, like one has the brilliant idea of saying, I can solve the classical case. And I'm able to solve idea. Let's generalize the things that I do here to this setting. It doesn't work here, it will work here, and then I will solve the polynomial identity testing, and everything will be done. But of course, as every time happens in mathematics, every time that you run after it or you invent some idea of the device, where like the computer with the route runner, it will just run away a little more. And then what this was discovered in the thing of the progress in this was that in the classical setting you have that perfect matching exists. If and only if there is not a hard block. If you don't have a hard block, you know that there will be a perfect matching, and vice versa. The problem is that when you pass to the continuous case, and this was due to Evangelios et al. In 2015, they realized that this is not true in the end. So there is a continuous perfect matching. This is not the same as there is not a corresponding hard block, and this is really problematic. And of course, the example, one needs an example for this, and usually the examples that one takes is antisymmetric matrices of order 3. So this is a linear superspace of matrices. One can check really easily that every antisymmetric matrix will have determinant 0. So no matter what you do in this space, everything will be 0. But when you try to check here the theory, you will realize that the hard block does not exist. So you cannot find here a hard block, but you can neither find a continuous perfect matching, so a non-singular matrix that lies in this space. And from here, not everything was lost, because what they proved was like, okay, if there is not a hard block, then they proved that at least for some sufficiently large 0, you can take your linear space, you can tensor it with a sufficiently large space, and then this will have a perfect match. So essentially by tensoring enough, so here you put the Kronecker product, you take some matrices, we tensor with some sufficiently large matrices, you do the addition, and then you will get a non-singular matrix. So this was what this was proven, and then this was realized by Bürgisser and Bürgisser. They realized that in the thing that is there, they also proved that this version of the problem is essentially the non-commutative version of the problem. So it's a little difficult to explain, and I'll leave an evaluation of the PET on the non-commutative case. Instead of evaluating numbers and matrices, you just pick matrices of arbitrary large size and you evaluate them, and if for some matrices this is evaluates to something different to 0, you know that this is formulation of 0. So here is usually numbers, because this is the commutative case. And in the non-commutative case, take arbitrary matrices and evaluate. So you get the translation to this case. And this, then there was another article by Bürgisser in 2003, and then by Garg et al. In 2016. And they showed that by a numerical algorithm, you can solve this. It was a version of a numerical algorithm of circum, which means you normalize the columns, you normalize the row, repeat this again. If the matrix gets made enough to double a stochastic matrix, then you know that the hard block is not there. Otherwise, you know that it has a hard block. So this algorithm is non-constructive, but this is long, more extremely fast than this algorithm here, that usually you end up blowing up dimension, and you have to pass with non-commutative algebra and a lot of another stuff. And now let's just find what we mean by hidden combinatorics. So the idea is that if one observes all this exposition here and everything else, one will realize that we only use this thing. So we only use how this linear correspondence, which technically is associated to a completely positive operator, moves linear subspaces around. You really don't look at this linear subspace. You just look how this operator here works. In the usual case, in convex geometry, this is enough to know the combinatorics, but the problem is that completely positive operators are a particular special. They are less than positive, so there are more restrictions. And the problem is that this does not characterize this linear correspondence completely. If this is one-dimensional, then you know by classical arguments in projective geometry that this is well-defined, and this will be characterized by this because this is just a projective map associated to it, plus something more. But in this case, no. And this, there is a very simple example. So one can take the whole space of 2 by 2 matrices, then one can take the span of this space. It's clearly that these two spaces are not different, but by some results taken to do on how this operator equality is defined, one can see that these two guys are equal, which essentially means that this can be bad news for this approach in order to solve polynomial identity testing, because a priori it's not even clear that just analyzing the combinatorics of these two maps that are the ones that we understand really well and for which we can do everything from the classical case to the quantum case or discrete case to the continuous case. Here, H generalization is more or less straightforward. You just pick the things, translate everything, and then you get the same results, more or less. So this is equality, so this means that it could happen, the possibility that we have spaces that have this same guy, but this, for example, has a non-singular matrix, but this doesn't have a non-singular matrix. And this is why I say hidden combinatorics, because essentially it seems that in quantum mechanics there is some part of the combinatorics that cannot be explained through the usual tools of convex geometry, or how positive maps act on lattices of faces. So essentially it means that there is some part of the combinatorics of this linear space of matrices that is just hidden somewhere, and you need really new ideas to exploit this part that is missing the passage from here to here. So in order to be able to differentiate these two spaces. Or in other words, linear algebra and quantum has more complexities than discrete, but this is more or less the big obstacle now, that understanding really if this is an obstruction to solving the polynomial identity testing or not.
In the beginning, that when you said that the polynomial identity testing problem can be reduced to this problem of finding non-singular matrices or something, how's the relation? So how do you get from these formulae to the matrices?
There is one argument of Balian that in which you do is you prove that there is some labelet graph in which you can prove that the determinant with some, and then some constructions you do like product or so other. But then there is this article of Kubres and Bürgisser, and they are doing the non-commutative case, and the idea is quite simple. It's just seeing how the inverse computes things, and then you do clever algebraic constructions. So you force that the right of entry of your inverse will just be the expression that you want. So essentially there is a way that if you have the sum, you can construct a matrix with these two matrices that give you the sum, then the product. So you start with the formula and then you start step by step. You construct this big matrix, which right of entry will be the same evaluation as the formula. And then there is an additional step in which you prove that till you enlarge this matrix a little bit, and then this matrix will be non-singular if and only if this non-top entry of this inverse of this matrix is non-zero. Essentially, it's a way of clever algebraic constructions. This is the of Kugel, but also you have, if you want a more combinatorial approach, then you have to look to Valiant. He does a lot of using graphs and do the construction more combinatorially.
So maybe I missed this point, but this example about the antisymmetric matrices shows that the one implication does not hold.
Yeah.
So what about the other implication? Does that hold?
Yeah, if you have a perfect matching, then you can have the other. That is essentially by the definition of this, because if this matrix is non-singular, then you know that this will have at least the dimension of W, because you know that here this the image of this AW, apply the image to this space, will be contained in this subspace. And if the dimension of this space does not go down, you cannot really do this, this construction here. Because this is also the same as saying that the dimension of H0 will decrease.
Okay.
So essentially, if you have a perfect matching, you really know that there is not a hard block.
Okay.
Maybe a bit more basic and naive. So I have a rough idea what the randomization of algorithms may be, but I'm not going to the connection to the polynomial identity testing. Can you explain a bit how these are related?
So this was, I mean, this is not a trivial result in the sense that the one for formulas is not, then you have these formulas that you also have a version for arithmetic circuits and a lot of other things. And then it was proven that if you can really do by Cabanets and Implagiasso, that if you can in some way do the polynomial identity testing in a fast way, then they use this construction with some clever manipulations of the permanent and other things, and they saw that they can construct a kind of lower bounds in complexity. And then the other way around was proven that if you can show lower bounds, then you can then randomize algorithms. So this is like the leap, because essentially if you are able to do this, then you will obtain lower bounds, but then in the same way these lower bounds will permit you to derandomize other algorithms. Because essentially, and also it's like the last problem that is still not the randomized. So primality testing was the randomized, other ones was the randomized. Apparently, the polynomial identity testing is the only one that is in the way of saying, okay, we are done with the important problems that we know probabilistically can solve, and we suspect. Because also there is one conjecture in complexity theory that is using random time will not get you down from polynomial, from exponential, non-polynomial time to polynomial time. And this is where all this plays into role.